0 is equal to n e to the minus x squared over 2a squared e to the I p naught x over h bar. Okay, so plugging that in here, we get an n squared, since we may as well assume that n is real. It really doesn't matter whether you assume n is real or n is complex, as long as the norm of the wave function works out to be 1. It doesn't matter. Okay, so then we have in here an integral dx. This guy here will come in 2 times squared, so it's going to be e to the minus x squared over a squared. And this I star, I'm going to get an e to the minus I p naught x over h bar. This will give me an e to the plus I p naught x over h bar. And the product of these two things is unity. This is a Gaussian integral, and now you know how to do a Gaussian integral. If you are ever stuck on a desert island and you have to do it in the sand, you can do it. And that comes out to be n squared root pi a squared. And that tells us what n is. Choose n so that this whole thing is 1. That means that n must be equal to 1 over pi a squared to the 1/4. Okay, good. So I can replace this with 1 over pi a squared to the 1/4. First thing we want to do is to figure out the expectation value of position. Here's the wave function. Have a shot. What do you think the expectation value of position is? What's the most likely position to find the particle in?
0.
0. Sure. This thing doesn't matter to the probability distribution. It'll go away when you take a complex conjugate. So all you got is this, and you're squaring it. So you got a probability distribution proportional to a Gaussian, which is centered at 0. Now the answer is 0 if I ask you. Right? I said 0, 1, or infinity. In this case, the answer is 0. Okay? X has to be located at. The expectation value of x should be 0. Now let's check it. Okay, expectation value of x, dx from minus infinity to infinity. By definition, it's this. X is 0. So that is 1 over the square root of pi a squared, integral minus infinity to infinity dx, x e to the minus x squared over a squared equals 0 immediately. Why?
Okay, it's an odd function times
Even times an odd function, exactly. X is an odd function. Goes from minus infinity to plus infinity. The Gaussian is an even function. When you integrate an even function times an odd function, you get 0. So just as you said, the expectation value of position at time t equals 0. Let's call it time t equals 0. The expectation value of x at time t equals 0 is equal to 0. Now we want the uncertainty in position. And to get the uncertainty, we will need delta x squared is equal to expectation x squared minus expectation x quantity squared. And since this is 0, it will be expectation x squared. So we have to get expectation x squared at time t equals 0. And that's not going to be equal to 0. Why don't we leave it for next time?